for coming. It's the last WNCG seminar of the semester. It's my pleasure to welcome Mary from CMU. She finished her PhD in the University of Michigan, and she's doing a postdoc at CMU. So.
Thanks for the invitation, and thanks y'all for coming. So I'm going to talk about fast matrix completion. This is joint work with Moritz Hardt at IBM. Okay, so matrix completion is a problem of finding low-rank structure in data. And so many of you might be familiar with the problem already, but if not, let me go through it slowly. So what do I mean by low-rank structure? My slides are not in okay. Enough of this is here. So what do I mean by low-rank structure? Maybe the canonical example of this is the Netflix problem. So let's say I have this Netflix matrix here, and on this side I've got movies, and on that side I've got people, and each entry in this matrix is how much a person likes a movie. That's like the matrix of Netflix ratings. And there's good reason to believe that this matrix ought to be pretty low rank, or close to a low rank matrix. And intuitively the reason for that is that, are we going to fix this?
This is just net. Oh. Oh.
How many
there
entries?
you go. Stay right there.
Does anyone have like a weight that was like a sandbag?
There's no fix, sorry.
It's mechanically pointed.
Can you move up the light?
That might not be.
Cool. Oh, very good enough. Cool. All right, thank you, Aaron. All right. So we have good reason to believe that this matrix might be low rank or close to a low rank matrix. Basically, intuitively, the reason is that which people like which movies is not all that complicated. There's only a few things that matter about movies and only a few things that matter about people to decide how much you're going to like a movie. There are some people who really like action movies and some people who really like romantic comedies, and it's not that complicated. And if you sort of squint and assume that this relationship is reasonably linear, this means that you can write this matrix as a factored matrix as a tall, skinny matrix. There we go. Okay, so like a tall, skinny matrix, where the skinniness is that there are sort of not too many attributes about movies that matter, and again here there's not too many attributes about people that matter. And in this problem, so this sort of recovering low-rank structure problem, the basic trade-off is you see only a few entries of the matrix. Not everyone rates every movie, right? And the goal is to, let's say, recover the entire matrix, or recover something about the matrix. So let's say you see who rates some movies, and some people rating some movies, and then you want to recommend movies to other people. And this general problem applies more generally not just to Netflix. So I guess collaborative filtering, sort of recommender systems, is one main application, but there are lots of other places that low-rank structure pops up in practice. So for example, I guess you might have heard of distance matrix completion. So for localization in sensor networks, if I have the entries in my matrix are pairwise distances, this matrix is going to be pretty low rank, and then I want to recover the whole matrix from a few observations. Like this. So that's the general problem. That's my blurb introducing the general problem. And then here's a slightly more formal version. So I'm going to make a lot of simplifying assumptions just for this talk. And none of these assumptions are necessary. It just eases up the notation. So let's assume for the rest of this talk that A is a matrix. It's symmetric, positive, semi-definite rank K. So it looks like this. I can factor it as a tall, skinny matrix U, and let's say the columns are orthonormal, and then a diagonal matrix sigma of singular values, and then U transpose again. So. And the assumptions here that I'm making are that A is square and symmetric and positive semi-definite, and none of these assumptions are necessary. It just eases the notation. In particular, the positive semi-definite is only there because when I say eigenvalue and mean singular value, no one will yell at me. There's no other reason that assumption is there. And we'll assume that this is close to that A might not exactly look like this, but it'll be pretty close. So there's some noise matrix N, which is going to be pretty small. And the problem is now I see M entries of A, so all the gray stuff I don't see, I just see the stuff in yellow. And I would like to recover the entire matrix. So about how many entries should I see? just to sort of have a benchmark in our heads, we would like the number of entries we have to see to be about k times n. So intuitively, this is because there are about k times n degrees of freedom, k times n numbers that live there, and so that's how many observations I should need to take in order to recover the whole matrix. And then the goal, like I said, is to find some a hat which approximates a, and by that I can mean a couple of things. So first, I might want a that is a hat that's close to a in spectral norm like this, or Frobenius norm if you like. So less than epsilon normalized appropriately, and then with some term that depends on the noise. Another thing we might want is to recover u itself, and the reason being, for example, in the previous slide, if u tells me what are those important features about movies or about people, then recovering these singular vectors tells me something about my data. What are the important features? And in that case, we might want to find some subspace u hat, so that the sign between the subspace spanned by u hat and the subspace spanned by u is not very big. So that's another goal we might have. Okay, so that's the basic setup for the matrix completion problem. Does everyone understand the problem? Okay, so I see some nods. So if you understand the problem, then you probably see also that it's completely impossible. Right? There's no way I can solve this problem. So here's a situation that is totally hopeless. Right? If I've got one really big entry and a bunch of 0 entries, and I have no idea what the matrix is, even if I know that it looks like this, right? And I have no idea what the matrix is, and I'm only allowed to make kn observations. If I don't know where that thing is, where the big entry is, I'd have to look at like n squared places in order to find it with any reasonable probability. And so I cannot distinguish this from the all 0 matrix, even though it is quite different because 1 followed by a bunch of zeros is a very big number. So because of that, I'm going to make an assumption. I'm going to assume that A is incoherent, which means kind of like spread out, so all the entries are kind of little. And I'll give a more formal definition of that later. Okay, so that solves that issue. This unfortunately is still impossible. So here's another example, which is problematic. So suppose that my matrix looks like this. So like all of these entries are 1. So they're not like 1,000 or 10 bajillion or whatever number I had there. They're all pretty small. And then a bunch of entries are 0. And then I sample some entries, and let's say that a bad guy samples them for me, and then the bad guy gives me n entries that live in this 0 section. Then I can't tell the difference between this and the all 0 matrix again. Right? So if there's sort of adversarial sampling, there's clearly nothing I can do. So we need to assume something about how I see these entries. And the solution is to assume you see random entries. And for now, I'll assume that you see sort of uniformly random entries. So each entry I'll see independently with probability p. And our goal will be to make p as small as possible. So those are our assumptions. And here they are again, just with slightly more notation. So the first assumption I made is that A is incoherent. That's the kind of flat assumption. So more formally, what I mean by that is that if A looks like this up here, so A is u times sigma times u transpose plus some noise, then I'm going to demand that each row of this u has small L2 norm. So that's pretty flat. So in particular, something like this. There's a parameter mu, which you can think of as a constant or something, which measures how big these are. And then I'm also going to assume some similar stuff about n. The noise matrix n can't be too spiky either for the same reason. And then the other thing I'm going to assume is that this set of observed entries is random. So each entry is included independently with probability. And I should say that these assumptions are clearly not valid all the time, especially in those examples that I gave before. But they are standard for this problem. There's been some work on relaxing them, in particular by many people in this room. But I'm going to just assume them for now, and sort of we can have this understanding that maybe they're kind of unreasonable, but it gives us a good starting place. So that's what I'm assuming. Okay, and the great thing is that now this is possible. I make these two assumptions, all of a sudden this totally impossible problem becomes possible, and this is well known and goes by the name of matrix completion. Okay, so there's a long line of work, sort of starting with Candace Recton and Tao. It's a beautiful line of work which basically shows that you can completely solve this problem with convex programming. So by running a convex program, you see about n times k entries of the matrix. That was about what we wanted. And basically get everything you want. the problem here is that this is slow. You have to solve a convex program. So the running time is, I guess, n squared is probably pretty generous, but it's certainly worse than that, right? It's a slow operation. On the other hand, there are a lot of things that have, I guess, until recently been heuristics, which go much faster, and one of those is alternating minimization. So alternating minimization, which I'll give a little more details in a little bit, is an algorithm for matrix completion that's much faster. So it's going to run basically in time linear in n. And recently there's been also some very nice work analyzing the performance of alternating minimization. And the guarantees look something like this. So if you take about this many samples, so here, this is the nk that we wanted. There's some polynomial factors in k. Let's ignore those for now. It's not important. And then there's this other term, which doesn't show up in the convex programming, which is the condition number of the matrix. So here, sigma 1 is the biggest singular value of my matrix A, and sigma k is the smallest. And this is sigma 1 over sigma k. So there's this polynomial dependence on the condition number there. And there's a bunch of other algorithms for matrix completion, which are very fast and work well in practice. And most of those don't have provable guarantees in our setting, so I'm not going to mention them right now. But if you want to talk about them, we can do that offline. Okay. But for this talk, I'm going to focus sort of on this dichotomy here. Basically, existing work either is slow, you have to solve a convex program, or there's this dependence on the condition number, which doesn't exist in the convex programming approach. And just briefly, this could be kind of bad, right? So if I think that I'm in some setting where my matrix is approximately low rank, then maybe the spectrum looks kind of like this, so it drops off kind of fast, but it's not exactly low rank. So in particular, there's lots of small singular values. So I might expect this to be quite poorly conditioned, so that this dependence is not desirable. And so the thing that I'm going to talk about now is a new variant of alternating minimization, which is fast. So it has the running time of alternating minimization, basically. So linear in the number of samples, in particular linear in n, the dimension of the matrix. And the number of samples needed depends logarithmically on the condition number. So the sample complexity is going to be something like this. So it's the same as that, except the condition number is now pushed inside the block. So that's the result that we get. And I should mention that recently in subsequent work, Jane and Netropoli have removed any dependence on the condition number when there's no noise. So that's pretty cool. Okay. Any questions before I? Yeah.
Just a quick clarification on the very last point. You're saying that the algorithm you're going to be presenting doesn't have any dependence on condition number if you already know it's noisy, so it's the same algorithm, or is it, or are they proposing a new?
Oh, they have a different algorithm.
Okay.
They're proposing a new algorithm. Yeah. Yeah, and it doesn't. I think the results don't hold for the noisy setting. Or they didn't prove it. The noisy setting might hold. Okay. So let me talk about the algorithm that I'm going to present is a variant on alternating minimization. So let me tell you about alternating minimization. So the basic, here's how alternating minimization works. So I have some matrix A, I see a few samples of it, and I want to come up with a factorization A equals U times V. And so basically I'm just going to go back and forth. I'll fix some U, let's say at random. I just pick U and fix it. And then my first step is to find V that minimizes this error. So this is the Frobenius error of A and U times V just on my observed samples. So with the subscript, I mean set all things that are not in my observed samples to 0. And then on the observed samples, do this, solve this optimization problem. And this is a least squares problem, so I can do this really, really quickly. All right, so I find that V really quickly. Okay, now I have V, and I fix it. And then I do the same for U. So now I have this fixed V that I got from the previous step, and now I go over to U, and I find a U that minimizes this. And I go back and forth for a little while. There it goes. And hopefully, after about log 1 over epsilon steps, I converge. That's the hope. Okay. So why does alternating minimization work? So here's the basic intuition from the analyses that we have. So one due to J. Netropoli and Sagabi, and one due to Hardt. So the basic intuition here is as follows. So let's pretend that I see all the entries. I'm going to cheat, pretend I see all the entries. Okay, so then what is the solution to this least squares problem? Well, you can work it out. Oops, or sorry, oh dear, wrong way. There we go. Okay, so I do this. What is the solution to this least squares problem? It turns out that basically it's just v gets a times u, appropriately normalized. I'm ignoring normalization. And then when I do the next step, basically u gets a times v. There's some normalization. And this is assuming, of course, that I see the whole matrix. So if I did see the whole matrix, which of course I don't, then the answer, then the answer to the question, why does alternating minimization work, is pretty easy. The answer is because it's the power method, right? Each time I just multiply by a, and there's some renormalizing that happens, and then I converge to the top k singular vectors. That's great. Unfortunately, it's not true that I see all the entries. So what happens if I just do this operation, but now only restrict to these entries that I see? Well, I get this same thing plus some error term. And so then the answer is, well, it's the Wootters power method. And one can analyze this. And I guess Eric has some of that. That's basically, and you can analyze this and work out how big these error terms are and show that this converges. So intuitively, what you should think is going on with alternating minimization is that as you run the algorithm, what's happening is that you have some subspace which corresponds to your estimate of u hat, and it's just getting closer and closer and closer and closer to the subspace you're actually after. So this is sort of the geometric view, just like it does in the power method. Right. So in particular, the principal angle between these two subspaces just gets smaller, goes to 0. And so that's the picture to have in mind, the geometric view. Okay, so now I should have waved my hands enough to convince you that alternating minimization is the best thing ever, and it always works, and where did the condition number come in? So why does this condition number show up at all in these analyses? It doesn't show up in the analysis of the algorithm at all too much. It shows up mostly in the initialization. So basically, if I want to have this nice convergence between subspaces, or at least if I want to prove this nice convergence between subspaces, I have to start suitably close. And in order to start suitably close, what's done both in theory and in practice, I guess, is to initialize not with a random subspace, so don't start with a random u or a random v, instead start with the u and v that you get by taking the SVD of the subsampled matrix. So I take this matrix and I have a bunch of non-zeros and a bunch of zeros, and I take the SVD of that, and that gives me some subspace, and I start alternating minimization from there. And that's enough to get me close enough, and then we have these provable guarantees. And the problem is that this SVD is the thing that depends on the condition number. So here's just a graph. This actually does matter a little bit. So here's some run of alternating minimization on a random matrix. If I start with a random initialization, it will flail around for a little while before it starts converging. And if I start with the SVD initialization, it just converges. So there is some effect. It might be that alternating minimization will always converge eventually. Okay. And the problem is that initializing with the SVD depends on the condition number, so that's where this comes in. So basically the problem is that in order to get this convergence, I need to start, my initial subspace needs to be close to my target subspace sort of on all of the directions, on all of the singular values, even the singular vectors, even those that correspond to very tiny singular values. So here's an example. So let's say that my matrix A looks like this. So I have some subspace spanned by the columns of U1, and some subspace spanned by the columns of U2. And the singular value associated with U1 is all 1, and the singular value associated with U2 is all 0.01, let's say, much smaller. Yeah.
So just to understand the scaling, even if I just had one vector I was looking for, I would want to be constant dot product, or 1 over root n dot product?
Constant.
Constant, okay. So constant condition number gives you constant dot product for the SVD? So I'm saying the
oh, how close do you need to be?
Yeah, so I'm saying the requirement for this to work is that you start...
You start constant close.
Constant.
So start 1 over 100 close.
Okay.
is good enough. Probably 1/4 even. It's good with the singular angle. Or sorry, the principal angle being, yeah, 1/4 is probably enough for alternating minimization. So, yeah, so just constant. But even with just constant, that's still a problem for this example. Right? So basically what I need is, right, I really want to capture U2, the second thing, even up to a constant amount, but that means that I need additive error in my approximation like 0.01. Because there's all this junk going on with the U1, and I need to get the U2, even though there's all this noise going on with U1. And basically that requires something like 0.01, 1/0.01 squared samples. And that's where the condition number comes in, is that if I want to get both of these at once, even if this guy is very small, I'll need a lot of samples. Okay, so that's the problem. Now let me just give you our fix to it. So for the rest of the talk, I'm going to focus on an example that's just only one level more complicated than that example I just showed you. So for the rest of the talk, my matrix looks like this. So there's no noise either. So there's one subspace spanned by U1, a subspace spanned by U2, and a subspace spanned by U3. And the subspace spanned by U1 corresponds to some really big singular value, sigma 1. And the subspace corresponding to U2, spanned by U2, corresponds to some kind of middle level singular value, sigma 2. And the subspace spanned by U3 corresponds to some really tiny singular value, sigma 3. Okay, so just 3 levels, and they're as big as you want. Okay? And I want to recover A using alternating minimization. Okay, so there's sort of 3 ways you could start thinking about this. So one is the way that I just mentioned, which doesn't work. So let's initialize with the SVD to approximate all of this matrix, even this tiny, tiny subspace, or the subspace corresponding to the tiny singular value. If I wanted to do that, I have to pay sigma 1 over sigma 3. That's what we're trying to avoid. Okay, not that. Another option is, well, okay, so let's just give up on this U2 and U3 business. Let's just initialize with the SVD just to approximate this sigma 1. And then I don't pay anything. Or, I don't pay anything above what I would be paying anyway for alternating minimization. So that's great. I haven't already messed everything up, but I haven't sort of recovered any decent approximation to these subspaces at all. So I can't just run alternating minimization starting from that. But I have gotten something. And then the third option, which is probably the best, is let's figure out how to make alternating minimization work, or prove that it works already without initialization or with a different initialization. And the problem with that solution is that I don't know how to do it. That's the only problem. Otherwise, I would do that. Okay, so we have these sort of 3 options here. 2 of them are kind of non-starters, so let's go with that one. All right. So let's show that if we start with that, maybe we can still make some progress. So the first idea you might think here is to do some kind of deflation argument. All right, so let's say I'm going to first not pay anything about the condition number and recover this first subspace. And then I'll subtract it off. Right? And then I'll repeat on this next matrix. Right? If I have truly subtracted off a good approximation, then what I have left here, the condition number, I can subtract off this block sigma 2 without paying the difference. Right? And then I repeat, and now I have this. So that's a natural idea. Unfortunately, it does not work, either in theory or in practice. And the reason is basically this. So this is my idealized picture of what would happen if I tried to do this deflation argument, sort of peeling things off. What actually happens is more like this. So I peel off the first thing, and then what I get is error. And my error, it turns out, is going to be on the order of sigma 2. So basically, I'm treating everything sigma 2 and below as noise, and so I can only really converge down to the noise, which is sigma 2. And so what I actually get now is U2, and then I get some error. And this error might be ranked twice as big as it was before. It might be it's U1 hat minus U1 actual. This might be rank U1 hat plus the rank of U1 actual. And it's on the order of sigma 2. So now instead of having just one little block on this order, I now have a much bigger block, much bigger subspace that corresponds to that magnitude of and then, well, I can still recover it, but now the rank might be twice as big. And if I try to recurse and do this again, in the next step the rank might be 4 times as big, and then the rank might be 8 times as big, and then at the end of the day the rank might be 2 to the k times as big. And so at the beginning I was waving my hands and saying, oh, constants don't matter, but 2 to the k is definitely not classy. We don't want that. So that's not going to be, so unfortunately that doesn't work. Okay, but actually it turns out that there is something that does work, which is only a slight tweak on that idea. So basically a soft deflation will solve the problem. So here's basically how our algorithm goes. And it's only very slightly different than what I said before. So I'll run through the algorithm now in this example. So the first step is to initialize with the SVD on just this first part. So you want to get some approximation, U1 hat, constant approximation. So this is exactly the same as before. And then run alternating minimization from there to get this first part. Same as before. So now I have an approximation, a pretty good approximation to the top chunk of this spectrum, or of the matrix. And then I subtract it off and I use SVD to initialize the next part. So before this is exactly like this failed algorithm. So far this is exactly like the failed algorithm. I haven't done anything new. And then here's the only difference. Now I'm going to run alternating minimization again, but instead of running alternating minimization just to sort of refine this guy on the second chunk, I'll just use this whole thing as an initialization and run alternating minimization from there. And so now I get some alternating minimization. Now I get some approximation x2 to the whole, first 2 chunks, and then I repeat. So now I will reinitialize. I'll subtract that off and run SVD to get an initialized thing here, and then I will use this whole thing to initialize alternating minimization. Run that again, right? And is there a question? Yeah.
So all these alternatives are with resampling, right?
Yes.
Yeah, and so so you don't need to run too many iterations of alternate. That's what you're saying.
Right.
I mean, how many do you need to run?
Oh, how many? So it goes
just for U1, like this when you find U1, how many do you need to run?
How many iterations do I need to run it for? So basically, I want to run it until the noise is on the level of sigma 2. So I will run it.
How do I find that one? I mean,
let's see. So it's in our paper. So run it like log 1 over epsilon, and then log sigma 2 over sigma 1, or log sigma 1 over sigma 2 times.
Okay, but it doesn't depend on epsilon. I mean, epsilon is the final error.
Oh yeah, sorry. Yeah. So run it until the error is like sigma 2. So yeah, log 1 over sigma 1. And that's where the logarithmic dependence in the condition number comes in. So when you add up all these ratios.
Right. So I'm sorry. How would you actually do it on a problem? I mean, how do I know when to stop?
That's a very good question. Let me finish. Actually, I think that's only like just another slide. That's a very good question. Yeah, I haven't answered that.
Good question. So convex optimization doesn't have any dependence on the.
Correct.
Okay.
Yeah. Yeah. So this still will have some dependence on the condition number for this reason that she just brought up, which is that I need to go until the error is like sigma 2, and that will incur something depending on the spectrum. But yeah, nominally we could. Ideally, there'd be no dependence. Okay, and so the punchline is that algorithm, just a little tweak, now that works. Modulo some stuff that I swept under the rug, like the answer to Zudia's question. So let me just briefly talk about what I didn't address in that brief overview. So the first is exactly how do we know where the gaps are? I don't know that my spectrum looks like this 3-step thing that I had for the easy example. And the answer is basically we use a good enough approximation to detect this with using SVD on the fly. So as we go, we keep checking to see is there a gap, and if it looks like there is, then we'll stop there and get that off. This is an issue because, and this is where most of those extra factors of k come from, because these gaps could actually be really small. So here's just a thought experiment. Imagine that my spectrum looks like 1, and then 1 minus 1 over root k, and then 1 minus 1 over root k squared, and then 1 over 1 minus root k cubed, and so on. So then the gaps between my singular values are all really small. But the condition number is huge. It's exponential, or it's like e to the root k in this case, right? And so I need to be able to detect gaps on the fly that are quite small, multiplicatively like 1 minus 1 over poly k. And that's where all these extra factors of k come from, mostly, is trying to figure out where those gaps are, even though they might be quite small. And one corollary of this, I'm not going to give all like the precise dependence in this talk, but if you look in the paper, you can see that actually the performance guarantees we have depends on what the spectrum looks like. So if the spectrum looks like this, that's pretty bad. If the spectrum has nice step things, that is better. For that reason. Another thing that I swept under the rug is that we need to ensure incoherence basically all the time, both between the iterations and during alternating minimization. So I run alternating minimization for a little while, I stop, now I want to do it on the next chunk after reinitializing. In order to get the guarantees for alternating minimization, I need these things to be coherent. Something happened to them, I didn't control it, who knows what's happening. And the solution is to basically very carefully truncate at appropriate steps and keep things flat. And similarly during alternating minimization. And so this is an issue with analyzing alternating minimization itself as well, not just this deflated version. You need to sort of ensure that during the algorithm things stay kind of flat. And for that we borrow a trick from previous work. So add some noise to make sure that things stay pretty flat. Okay, so that's all the stuff I swept under the rug. But modulo that, let me state a theorem. So here's what we show. This is in the exact case when there's no noise. What we can show is this, and let me step through it. The hypotheses are those assumptions that I said before. So let's suppose that every entry is included independently with probability p, and that my matrix is incoherent. And let's say that and here I mean incoherent with parameter mu, and let's just say it's a constant, just to avoid cluttering up this slide with more parameters. You can find all the parameters in the paper. And let's say that my matrix is exactly rank k. So then the punchline is that there is, we can sample about this many entries. So here, that's what I claimed before, so something linear and polynomial in C and logarithmic as a condition number. And we return some xy that satisfies this thing that we wanted. And you can also get that the subspaces are close as well. Yeah.
So where does the dependence on the gaps in the spectrum come in here?
So I've not stated them in this version. Where it would come in basically is in the dependence on k. So the dependence on k is worse if the spectrum is kind of like I described, that worst case, and it's better if it's more blocky. Right, and the dependence on k is much better if it's just all flat. Yeah.
What is C in the worst case?
9. There's a reason I've avoided saying it out loud until now. Yeah. In the worst case, if everything is as bad as it could be, C might be, I think, yeah, 8 or 9. That's a good question. Yeah, so that's unfortunate. Okay. So now let me complicate this up a little bit and say what happens when there's noise. So now same assumptions, but now A is u times v transpose plus a noise matrix. Okay. And now there's 2 new terms that appear in the number of samples that I need. One term is this guy here, which depends on the Frobenius norm of the noise matrix. So that makes sense if this is like the noise and this is the signal. And if that gets too big, then you need more samples. And the other term that shows up is this gamma k, which is defined like this. So this basically depends on the last singular value that you want to call as part of the matrix, and the first one that you want to call as part of the noise. If there's a big gap there, that's better for us, and if they're really close, that's worse for us. This makes sense. And so basically this, if there is no noise, if the gap is really big, this gets close to 1, gamma k gets close to 1, it doesn't really matter. And if this gap is really small, if sigma k plus 1, the top singular vector of the noise, is really close to the bottom singular vector of the matrix, then this sigma k is really small and is bothersome. Yeah?
Is your noise random or is it worst case?
Worst case. Yeah, anything with Frobenius norm. Any other questions?
If it were something like random, then could you do something to avoid paying the Frobenius? Because then it would basically mean.
Yeah, so I'm sure you could do much better if the noise is random. Honestly, I haven't thought of that. I haven't thought about it. But yeah, I'm sure you could do better.
Following up on the assumptions on noise theme, another thing you could assume is that the top singular value of the noise is less than sigma k. Because, you know.
I mean, of course it's less than.
Okay, so you have that as
I'm saying, yeah, you're right. Right, so if I'm writing A like this, I might as well write this in the best way possible, right?
Yeah.
So UV transpose is the best rank K approximation to A, and then the.
So you can impose an assumption, if you want to call it that the top singular value of n is less than sigma k.
That's right.
And you do that.
Yeah. When I write it like this, I mean this
Okay,
is the best way to write it like that. Yeah. I see. Yeah. So I guess by sigma k plus 1, what I mean here is the top singular value of the.
No.
Yeah, that's a good point. I bet that things would still work if I didn't want to write it, make that assumption and write it like that, but we didn't work it out in that case. I think it would probably be fine. Are there any other questions about all the symbols up there? Okay, so let me just very briefly go over the proof idea. So I basically kind of did it when I went through the algorithm, but I'm just going to walk through the algorithm again, this time with extra bubbles floating around it, sketching the proof idea. So the basic idea, ignoring all of those things that got swept under the rug, is just a pretty simple inductive argument. And I'm going to maintain the following inductive hypothesis, that at each step t, I can consider how close my recovered, this notation hasn't been properly defined, but I'm going to look at my approximation of the ith chunk of the spectrum and compare it to the actual ith chunk of the spectrum. And I want that error, so as measured by the principal angle between those subspaces, to be small. And how small do I want it to be? I want it to be about as small as the next chunk. Right, so before I said we'll converge on sigma 1 until it's down to about the noise level of sigma 2. So here, the error in the ith chunk for I less than or equal to t is about sigma t plus 1, so about the magnitude of the n. And I start out initializing with the SVD on this top chunk, and what the SVD guarantee gives me is something like this. So the error is not as small as the next chunk, it's constant. So some constant fraction of sigma 1. And that's what I need to initialize alternating minimization, that the error is a constant fraction of sigma 1. Okay, so now I run alternating minimization down until about the level of the next chunk, sigma 2. Okay, so now my inductive hypothesis is satisfied. All the errors in sight, there's only one chunk, is about sigma 2. Now I initialize the next chunk. Now the error here is about on the order of sigma 2 after I've initialized it. The error here is about on the order of sigma 2 by induction. And now the error on this whole thing is about on the order of sigma 2. And so now when I run alternating minimization using this whole thing as the initialization, that will converge down to about sigma 3. So that's the next step. I run alternating minimization, and my guarantee goes down to error on the order of sigma 3. Okay, so now the inductive hypothesis is satisfied for the next step. And I guess I've animated one more round of this, but you can see how it goes. So in the next chunk, I recover sigma 3. It gives me a guarantee that the error there on that chunk is about on the order of sigma 3. By induction, my error on sigma on the x2 part was also about on the order of sigma 3, and now I run the whole thing, and I get down to something at the error of sigma 4, and so on. And this allows me to keep going, and at each step I accrue sort of a log sigma I plus 1 over sigma I for precisely the reason you mentioned before. That's how many steps I need to run alternating minimization to get down to that error. And then at the end of the day, what I have left is log the condition number. Okay, and then we're done. I went faster than how, yeah.
So what happens if you run every step log 1 or epsilon times? If you run each iteration log 1 or epsilon times, can like your dependence on condition number vanish?
So certainly the dependence on the condition number will vanish, but also the guarantees will vanish. So like if I run each step for log 1 over epsilon time, then I'll guarantee that I converge to within epsilon.
Yes.
But it might be that
so if you
like sigma 2 is less than
in such case you don't care. Right? Like if my remaining singular values are less than epsilon, I don't care. I want only epsilon accuracy.
Right, well, so this depends, right, I guess this depends a lot on what kind of error metric I'm considering. So you're absolutely right if I want that, like, the norm of A minus what I recover to be smaller than epsilon. The other thing that I said was, what if I want these subspaces to be within epsilon of each other? And in order to get that, and that's actually what we recovered, this is stronger. In order to get that, then that doesn't work. Does that make sense?
Yeah, it makes sense.
Yeah, that's a really good question. Yeah, so there it's kind of key that we're after this subspace, we're after this structure. Are there any other questions?
So when you initialize U2, right? So you have similar values of order sigma 2 in both the error matrix and in the actual matrix. So how do you distinguish that?
Say again?
So after you do A minus A1, right?
Mm-hmm.
So in that matrix you have similar vectors corresponding to sigma 2 in both the error matrix as well as in the actual residual matrix. In A minus
Yes, that's
A1,
right. Yep.
So there is an error matrix with singular value of the order of sigma 2, and then there is a residual matrix with the largest singular value of the order of sigma 2.
Mm-hmm. Yeah.
Right?
And
so do you take, when you're initializing, when you're taking the SVD and take the top k, how do you know that it is the singular vector directions of the residual matrix and not the error matrix?
I see. Right. So now so that's kind of why I'm going to add back in this x1.
Don't we run it till the error is less than sigma 2 by 100?
Yeah, that's true, but that doesn't.
And therefore automatically the sigma.
So the sigma 2 will pop out, not the. I mean, when you do the second step, just like isn't that the answer?
Yeah.
Is that? Sorry, I'm not sure I completely understood your question, but has it been answered? Or is it okay? I'm sorry. We can talk offline because I want to understand the question as well as the answer, apparently. Yeah. Okay, so let's talk offline. Are there any other questions? Okay. Yeah, so I appear to have gone much faster than I expected. Done early, but let me just conclude. So what I talked about was a new soft deflation variant of alternating minimization, and this is fast. So the runtime is linear in n, so it's much faster than convex optimization, and the sample and time complexity is logarithmic on sigma 1 over sigma k. And so there's a number of open questions. I think that the most interesting one is how does alternating minimization itself actually, can you prove that alternating minimization itself actually works okay without dependence on the condition number, or with logarithmic dependence on the condition number? So in practice, it seems to work pretty good, and we can't prove it, and I think that would be really interesting. And then, as Rachel pointed out, my embarrassing constant of 9, this would be good to improve. And actually, in most other analyses of just alternating minimization, even there is some not quite as unmentionable, but still not entirely mentionable constant in power of k that would be good to reduce. Is there a question?
Yeah, going back to the previous
Okay.
thing. So again, it's following up with the same question.
Oh dear, but we've already established. Okay, maybe I'll understand it.
But
Say it. Yeah.
So it comes down to you're stopping with sigma 2 by 100 or sigma 4 by 100 or whatever.
Mm-hmm.
How do you know sigma 4? So that begs the question, how do you know when to stop?
Right. So that's sort of all of the stuff that got swept under the rug. So here I was just sort of giving the outline of the proof when I know what the spectrum is and I know it's a step function. So in actuality, what happens is that as a pre-processing step, when I run the SVD, I look to estimate these gaps. Oh, maybe this is the answer to your question. Or this is now I understand why what you said is the answer to her question. So I estimate down to like sigma 4 over 100 or something, and I can see if the next thing is going to be much smaller than that, plus or minus sigma 4 over 100. And so using this like kind of shaky approximation that I had from last time, I can sort of see where the spectrum should be.
But this then comes back to the figure, the worst case diagram. What if everyone was just, there's no steps, but everyone was just a little bit off, just going down all the time?
Oh, okay. In that case, turn 100 into 100 times k to the 100, or k to the 9. Yeah, right.
Okay.
Yeah, exactly. So that's like I said before, that's where a lot of these extra powers of k come in. So instead of, I said 100 here for my easy exposition, but you're absolutely right. So go down to 100 over some power of k. Does that solve? Okay. Yeah.
You have a better visualization. Did you see any like synthetic experiments where it actually performs better?
Yes, that's a great question. Yes. So here, let me show you a picture. Right, the answer to your question, I like your question, was can you make synthetic experiments where this actually performs better? And the answer is yes. The question is like, can I necessarily come up with very natural experiments?
No, I didn't ask that.
But I like the question you asked. Here's an example. So I think the answer is that this performs better when you do have these big gaps in the spectrum and you sort of maybe have some idea about where they are. So here's an example maybe of how alternating minimization performs, and then we can see how our algorithm improves on it. So here's a run of alternating minimization. This is a random 1,000 by 1,000 matrix with, it's that example that I gave in the first half. So the first 3 singular values are 1 and the second 3 are 0.01. What happens, so this is just alternating minimization from a random starting point, is these top, so I'm plotting a sine of the principal angles. So there are 6 principal angles. So here's the top 3, the ones that correspond to the singular value of 1. So it does this flailing thing that I said for a little while, and then it starts converging. And it converges until the error is about 0.01, the sort of the level of sigma 2, at which point these guys start getting picked up in the noise, and there's some flailing that happens here, and this flattens out for a little while until this flailing is dealt with, and then everybody starts converging. So that's sort of how alternating minimization works. Here's alternating minimization with an SVD initialization.
Sorry, just one question with the previous one.
Mm-hmm.
So that's alternating minimization started from a random.
Random.
What about alternating minimization started from a simple SVD?
Here it is. Yep. Good question. I like your questions. Yeah. So here's alternating minimization started from SVD. And what happens here is that sort of this first flailing stage is mitigated. It doesn't happen. We just start converging immediately. But the second flailing stage still happens, right? So when I get down to about the order, 0.01, about the order of the sigma 2, then this thing kind of, I haven't done the SVD here, and this has to, flail around for a little while until it figures it out, and correspondingly this. And so what our algorithm does, basically all it's doing is just reinitializing with SVD at the key points all the way down. So here's our algorithm running on this same matrix. Then you get basically the same thing happens, except at some point, in this flailing, it figures out there's a gap there, reinitializes, and starts converging. And so in this case, at the end of the day, our algorithm does better than initializing with SVD, which does better than non-initialized. Yeah.
So you're basically better than the green curve as long as you have a good estimate of where the gaps are, like you said.
Well, so our algorithm found this itself. So I didn't tell it.
There's a detection step?
Yeah, via this detection step that I was waving my hands about. But I did have to. So that this is why I didn't include this picture in the main slide. Is that this particular example is like the extra nice one, the one where I have 3 good ones and then a big gap and then 3 other ones, and so the detection happens very easy. I think if it were worse, maybe it's not. I wouldn't get such a.
So are you talking about the initial step where you take the original matrix A with all the erasures and you just take SVD on that? That's the detection you're talking about?
Yes. So on the fly. So we were taking the SVD of these matrices to initialize a lot, basically every time.
Right.
And each time we do that, we're doing it with sort of a different level, at like a different level of fineness.
I see.
And then using that level of fineness, we can identify the next gap.
So every time you look for the next gap.
Exactly. Yeah.
Okay.
And that's how you figure out where the gaps are. Yeah.
Is there any situation, or can you construct an example where these intermediate SVDs actually hurt you as opposed to help you, or you will always match alternating minimization?
These questions are amazing. Yeah. So here's a picture of. So this intermediate SVD, I guess here it actually does help in the long run, but in the short term it helps up there and hurts down here. This is just another picture of just slightly different parameters. It's a bigger matrix. So that's.
So it hurts you locally, but you didn't lose to AM still, right?
Yeah, I didn't.
Okay,
Yeah.
So there's no case where you actually lose to AM?
No, I think there are some cases where we lose to AM just because of this overhead that you have to find the gaps. So I think if the spectrum were.
So you could be doing SVD many, many times?
Yeah, you could when it's just not needed, yeah. So I think that there are definitely situations where this is worse than AM by a factor. But there are some situations where it's better. Like clearly the pictures that I've chosen to display are the ones where it's better.
But you're plotting iterations, not so some of your iterations are more expensive, namely the ones where you have to do SVD.
Oh, no, so I'm using, I think with these ones I normalize it so I have the same number of samples for SVD iterations, the same number for AM iterations, just to make.
But I mean, you could be doing an SVD at every single iteration.
And I think he's asking computational running time.
Okay.
Yeah.
Yeah, running time. That's a good question.
Right.
Yeah, I don't have, you've run out of questions that I have picture answers for.
Oh, but then sample complexity-wise, back to Alex's question, is it possible that it would be worse than alternating minimization? Your scheme? So
I think so. The same answer that I gave to Alex. That so in this picture, the iteration and the sample complexity are mapped the same because in my different iterations, I'm using the same number of samples. And I think that there definitely are cases that you could cook up where our algorithm would do worse than alternating minimization.
For alternating minimization, if you reuse samples, what happens?
So. Yeah, there's a difference between yeah, well, so you should know that I'm not the one to ask about what happens in practice.
Show your plot.
Okay, that's true. I did write some code. But yeah, so it does perform a little bit. Basically, it performs pretty good. I think. Is it that's your experience as well, like other matrix completion?
Yeah, I mean, you'd never do resampling in practice.
Yeah, in practice, the resampling seems pretty. Not necessary for analysis, it depends. So there's this work that I mentioned earlier, Jane and Netropoli, and so it works for exact matrix completion, so for no error, and they don't reuse samples. And I'm not familiar enough with that paper to tell you how they do that, but they have some analysis where they can show that by not reusing samples, it's not alternating minimization, it's a different algorithm that they can do with that. Yeah, so I think that is a good theory question also, is proving that alternating minimization works well without reusing samples. Any other questions?
So how realistic is this assumption that you see random entries?
I mean, so not at all, right? There are two answers to that question. So one is like maybe you would hope that, well, so in some settings, I'm doing the sampling, and I can choose how to sample, right? In which case I can sample randomly if I like, and then that's a perfectly good assumption. There are some situations people don't rate movies at random. That's not true. In that case, it's not a very good assumption, but things seem to work anyway. And so, like I said, there has been some work relaxing those assumptions, and so I guess of the people sitting in this room, I'm not the expert on this, but my understanding is that you can relax, if you relax the incoherence assumption, you can also relax the sampling assumption at the same time, so sort of sampling by leverage scores or something, that you can also do that. But yeah, that's an important point. These assumptions that we're making, while standard, are not good, and I think that there's a lot to be done in understanding how far you can push them.
Is the dependence on incoherence same as what we'd expect?
Yeah, it's like mu squared.
Any other questions? Okay, that's time.